There are moments in science that change how we see the universe. The invention of the telescope revealed worlds beyond Earth. Spacecraft carried us to the moon and across the solar system. Today, another discovery may one day join that list. On the surface of Mars, inside a carefully sealed titanium tube, lies a small sample of rock collected by NASA's Perseverance rover. At first glance, it looks ordinary. Yet this single piece of ancient mudstone could hold one of the most important scientific questions humanity has ever asked. Did life ever exist beyond Earth? Recent headlines have suggested that Perseverance may already have found evidence of ancient Martian life. Those headlines are exciting, but science moves more carefully than news stories. Extraordinary claims require extraordinary evidence, and researchers have learned through decades of exploration that Mars often presents clues that seem biological before turning out to have entirely geological explanations. That is why this story deserves a closer look. Rather than asking whether life has been found, a better question is this: what exactly did Perseverance discover, and why are scientists paying such close attention? To answer that, we first need to understand why the rover landed where it did. When NASA selected Perseverance's landing site, it wasn't searching randomly across the Martian surface. Scientists were looking for a place where life, if it had ever existed, would have had the greatest chance of surviving and leaving evidence behind. The answer was Jezero Crater. More than 3.5 billion years ago, Jezero looked very different from the cold desert we see today. Geological evidence shows that it once contained a long-lived lake, fed by rivers flowing down from the surrounding highlands. Those rivers carried sediment into the basin, creating a large delta remarkably similar to those found on Earth. Orbital spacecraft can still see the outline of those ancient channels today. They have also detected clay minerals spread across the crater floor, minerals that form only after prolonged contact with liquid water. On Earth, environments like these are among the best places to preserve traces of ancient microbial life. That made Jezero one of the most promising locations on Mars. Perseverance landed there in February 2021 with a clear objective. Rather than searching for living organisms, its mission is to study rocks that formed billions of years ago and determine whether they preserve chemical or mineral evidence of an environment that could once have supported life. The rover carries some of the most advanced scientific instruments ever sent to another planet. Its cameras reveal microscopic textures in rock surfaces. Spectrometers identify minerals and chemical elements with remarkable precision. Most importantly, Perseverance can drill cylindrical rock cores, seal them inside sterile titanium tubes, and leave them on the Martian surface for a future mission to collect and return to Earth. That final step is crucial. Many questions simply cannot be answered using instruments carried by a rover. Some analyses require laboratories far larger and more sophisticated than anything we can currently send across millions of kilometers of space. During its exploration of Jezero Crater, Perseverance gradually worked towards the remains of an ancient river system known as Neretva Vallis. Then, in July 2024, it encountered a rock unlike any it had examined before. Scientists named the rock Cheyava Falls. At first, it appeared to be another piece of ancient mudstone, deposited quietly on the floor of a lake billions of years ago. But when Perseverance began analyzing it, something unusual emerged. Two instruments played a central role. Pyxl maps the chemical composition of rock with microscopic precision using X-rays. Sherlock uses laser spectroscopy to search for organic molecules and identify minerals associated with environments that may once have been habitable. Together, these instruments provide an extraordinarily detailed picture of Martian geology. The results immediately attracted attention. Cheyava Falls contained organic carbon compounds embedded within fine-grained sedimentary rock. Organic molecules alone are not evidence of life. They can form through completely natural chemical processes. Meteorites also deliver organic material throughout the solar system. What mattered was not simply that organics were present. It was the combination of features found together in the same rock. Tiny dark spots, only fractions of a millimeter across, appeared scattered throughout the sample. Each one possessed a distinctive chemical structure. The centers closely matched the surrounding rock, while their outer rims contained elevated concentrations of iron and phosphorus. On Earth, similar microscopic structures are frequently associated with microbial activity. That observation alone proves nothing. but it was enough to make scientists investigate much more closely. The discovery became far more interesting when scientists looked beyond the organic molecules themselves. Inside Cheyava Falls, Perseverance identified two minerals that are uncommon on Mars, but well known to geologists on Earth: vivianite and greigite. Individually, neither mineral proves the existence of life. Together, however, they raise important questions. Let's begin with vivianite. On Earth, this iron phosphate mineral commonly forms in water-rich environments where oxygen is scarce. It is often found in lake sediments, riverbeds, and wetlands. In many of those locations, microorganisms play an important role in the chemistry that allows the mineral to develop. Some bacteria survive without oxygen by using iron instead. Rather than breathing oxygen as we do, they gain energy by converting iron from one chemical state to another. This process, known as iron reduction, leaves behind chemical signatures that can eventually produce minerals such as vivianite. These microorganisms require no sunlight. They can live deep underground or beneath lake sediments, wherever water, carbon, and chemical energy are available. Greigite tells a similar story. This magnetic iron sulfide mineral often forms in environments where microorganisms reduce sulfate into sulfide. When sulfide reacts with iron dissolved in water, greigite can crystallize within the surrounding sediment. Again, this mineral is not exclusive to biology. Purely geological reactions can also produce it under certain conditions. But in Cheyava Falls, both minerals were found together, alongside organic carbon, and within microscopic structures that resemble patterns frequently associated with microbial communities on Earth. That combination immediately caught the attention of astrobiologists, not because it confirmed life, but because several independent observations appeared to point in the same direction. If only one of these features had been present, the discovery would have attracted little attention. Organic molecules alone are common throughout the solar system. Iron minerals can form without biology. Microscopic structures can also result from geological processes. Science rarely relies on a single clue. Instead, researchers ask whether multiple independent lines of evidence all support the same explanation. That is precisely what made Cheyava Falls so intriguing. Even so, the Perseverance team remained cautious. Every unusual observation must first survive the most difficult test in science. Could there be a simpler explanation? Researchers immediately began examining every geological process capable of producing the same minerals without involving living organisms. The first possibility involved volcanic activity. Hot fluids moving through underground rock can drive chemical reactions that create minerals similar to those observed by Perseverance. If ancient hydrothermal systems once existed beneath Jezero crater, perhaps they produced the chemical signatures without biology. But the surrounding rocks offered little support for that idea. Scientists found no evidence of the high temperatures normally associated with hydrothermal activity. The mineral layers remained remarkably well preserved, showing none of the alteration expected if intense heat had passed through them. Another explanation focused on chemistry alone. Under laboratory conditions, certain reactions between sulfates and organic compounds can generate minerals similar to greigite without any biological involvement. However, these reactions require temperatures far higher than those indicated by the geology surrounding Cheyava Falls. The rocks simply do not appear to have experienced those conditions. Researchers also considered whether highly acidic water might explain the unusual chemistry. Acidic environments accelerate many mineral reactions and could potentially account for some of the observations. Then Perseverance found another important clue. Nearby lay deposits containing olivine, one of the most chemically fragile minerals found in volcanic rock. Olivine dissolves rapidly in acidic water. If the ancient lake had been strongly acidic for long periods, very little olivine should have survived. Yet Perseverance found it preserved remarkably well. That discovery suggested the water in this region had probably been relatively mild rather than highly acidic, weakening another non-biological explanation. Little by little, several geological alternatives became increasingly difficult to support. None could fully explain every feature observed inside Cheyava Falls. That does not mean biology is the answer. It simply means that the question remains open. And in science, unanswered questions are often the beginning of the most important discoveries. Despite the excitement surrounding Cheyava Falls, the Perseverance team has been remarkably careful in the way it presents its findings. That caution comes from experience. Mars has produced several discoveries over the past 50 years that initially appeared to point toward biology, only for later research to reveal entirely geological explanations. Every generation of planetary scientists has faced moments when the evidence seemed convincing, yet further investigation told a different story. Those lessons continue to shape the way researchers approach every new discovery today. One of the best-known examples dates back to 1976, when NASA's Viking landers carried out the first direct biological experiments on the Martian surface. One instrument added nutrients containing radioactive carbon to samples of Martian soil. If microorganisms were present, they would consume those nutrients and release radioactive carbon dioxide as a byproduct. To the surprise of many scientists, the instrument detected exactly that response. For a brief period, it appeared that humanity might already have found life on Mars. Years later, however, another mission revealed that Martian soil contains large amounts of perchlorates, highly reactive chemical compounds capable of producing almost identical results without any biological activity. What once seemed like evidence of metabolism eventually proved to be an unexpected chemical reaction. A similar story unfolded in 1996 with the discovery of the Martian meteorite ALH 84001. Under powerful microscopes, researchers observed tiny elongated structures that resembled fossilized bacteria. The announcement attracted worldwide attention, and even the President of the United States addressed the discovery publicly. But as analytical techniques improved, scientists found that the same microscopic features could form naturally through water-rock interactions known as serpentinization. Once again, Mars had produced something that looked remarkably biological without requiring life at all. This history explains why researchers refuse to describe Cheyava Falls as proof of ancient Martian organisms. Instead, they call it the strongest potential biosignature ever identified on the planet. That distinction is important. A biosignature is not evidence that life certainly existed. It is an observation that is consistent with biology while still allowing for other explanations. The goal of science is not to find the most exciting interpretation first. It is to eliminate every alternative until only one explanation remains. The next step is both simple in principle and incredibly difficult in practice. Bring the sample back to Earth. Perseverance has already drilled a core from Cheyava Falls and sealed it inside a sterile titanium tube, where it now waits for a future Mars sample return mission. Only in laboratories on Earth can scientists perform the precise analyses needed to answer the biggest question of all. They will study the sample's carbon isotope ratios, search for complex organic molecules, and look for chemical signatures that, on Earth, are closely linked to biological activity. No single experiment will provide a definitive answer, but together they could reveal whether these remarkable rocks were shaped by geology alone or by something that was once alive. Returning those samples remains one of the greatest engineering challenges in planetary exploration. The mission has faced delays, rising costs, and uncertainty, yet it continues to be regarded by the scientific community as one of the most important goals in modern space exploration. Until those samples reach Earth, the mystery of Cheyava Falls will remain unresolved. Whatever the outcome, this discovery is already significant. Mars preserves a record of the early solar system that Earth has largely erased through billions of years of geological activity. By studying these ancient rocks, scientists are learning not only about Mars, but also about the conditions that existed on our own planet before life emerged. If future analyses confirm that life developed independently on Mars, even in its simplest microbial form, it would transform our understanding of the universe. It would suggest that life may not be an extraordinary accident, but a natural outcome wherever the right conditions exist. If, on the other hand, the evidence ultimately points to an entirely geological explanation, the discovery will still deepen our understanding of how planets evolve and how complex chemistry can imitate biology. For now, the answer remains sealed inside a small titanium tube on the surface of Mars. It is one of the most carefully preserved scientific samples ever collected, carrying a question that humanity has been asking for generations. Are we the only world where life ever began? For the first time, we may finally be close to finding out.